Hey everybody, in this video I'm going to show you how to solve problems using energy, and we're going to start off with isolated systems. So first of all, we should say what an isolated system is. An isolated system, or an IS, is a system where energy can't leave. So energy cannot leave the system. And I guess you're probably wondering, well, when is it possible that energy can leave a system? And that happens when you have friction that generates heat, and heat can leave the system, and that energy is no longer available. So isolated systems and physics problems are usually problems that don't have any friction. So I'll just say, typically, right? Typically, no friction. Okay, so let's just go with that for now. And what I'm going to write down next is the idea that if you have work that's being done within a system, that we're going to assume that all that work is being done by conservative forces. Okay? So the conservative forces are forces that have their own forms of potential energy. The two examples of conservative forces are gravity and spring. Okay, so those are the two main conservative forces, and a lot of problems really involve just one or both of those forces. Okay, so let's see where that takes us, right? So this is the statement that I wrote here: work is net is equal to the work done by the conservative forces. What we can do with that is we can actually do a replacement on each side. We know that the work done by the net force is equal to a change in the kinetic energy of an object. We also know that the work that's done by conservative forces is equal to a negative change in the potential energy that goes with each of those forces. And so we're pulling together those two ideas here. And I'm going to get these two change terms on the same side. And I can do that by adding delta U like that. And what I just wrote is actually a statement, one way to state that mechanical forms of energy are conserved. So mechanical forms of energy are conserved. And mechanical forms of energy, well, they're basically gravitational energy and elastic energy from springs. So those are the two forms that we've learned about so far, and they go along with the gravity force and the spring force. I'm going to put a box around this, right? This is important. And what that says is that, if you have, for example, a change in potential energy that's a decrease in potential energy, in other words, if you have a negative potential energy or negative change, like you lose some potential energy, well, what's going to happen is that the kinetic energy is going to have to compensate for that. It's going to have to increase, because that's the only way these two things are going to cancel. Conversely, if you have an increase in potential energy of some kind, that means the object or the system has to lose kinetic energy. So these things kind of go together. And that's one way of saying that energy is conserved. Okay. I'm going to write this formula in the box in a different way. You might like this better, I don't know. But I'm going to use initial and final. So delta K is the same thing as K final minus K initial. And delta U would be U final minus U initial. So kind of expanding that out. And you'll see right away that if you group those terms, and you put the finals, you keep the finals on the left side, and then you move the initial terms over by adding them, you get another way of writing this conservation of energy formula. And I'm going to draw a box around it. Oops. And that basically says that whatever total mechanical energy you start with, in other words, K initial plus U initial, if you add up the joules of both, the total number of joules should be equal to the total number of joules at some later point in the system. So at some final point. And this is just a different way of saying that mechanical forms of energy are conserved. So both of these formulas are really the same thing, but what you notice about them is that they basically just include kinetic energy and potential energy. Later we'll learn about non-isolated systems or open systems that involve thermal energy and other things. But for now, this is a good starting point. All right, so make a note, put a box around that equation and around that one. Let's just put this onto a problem. Let's try it on a problem. And I'm going to draw a side pull Atwood machine. So we have a table. We're going to put a cart up here on wheels. Let's give that cart, I don't know, a mass of 2 kg. And then we're going to put a pulley with a string over it, dropping down. And the mass over here is going to be, let's say, 1 kg. And then let's say that that 1 kg mass, it's going to fall to the floor. And let's just say that it's going to fall vertically by maybe 3/4 of a meter. It's 3/4. Okay. Assumptions, well, no friction in the pulley, no mass of the pulley. The string doesn't stretch. And how about we assume that there's no friction? So the coefficient is 0. So that top car is just going to roll. So, a question in a physics problem might be something like this. It might say, if you start from rest, so start at rest, right, find the velocity. I'll call it v final. But what I mean by that is find the velocity just before that 1 kg object hits the ground. Okay? So the system is starting at rest, and v final is going to happen right before this hits the ground. Okay, so why don't we set this up with this is an isolated system. There's no friction, so you only have kinetic and potential energy. So we can do K initial plus U initial is equal to K final plus U final. And let's look for some easy zeros, okay? Well, one easy zero that I see is that the initial kinetic energy must be 0 because neither one of these carts is moving. So by initial here, what we mean is the initial part is when this is when it's at rest, right? So the 2 kilogram cart has 0 kinetic energy. So does the 1 kilogram object. So those both have 0 joules. Now for potential energies, well, you could say let's focus on the 2 kg, right, up here. And you might say, well, the 2 kg has potential energy, doesn't it? Because it's way up high, right? It's really far above the ground. It's like this height above the ground. But we don't even know what that height is, right? And we don't care too much because that 2 kg object never leaves the table. So it never has a change in that potential energy. So if you want, you could say that's almost like a constant, right? I'll write it, but that constant would be the energy of that top cart as it rolls across. The the dropping mass does have a potential energy, and so that's going to have a potential energy. Let's measure that going from the ground up, right? So we'll just say from there to there, and that's 3/4 meter. So that's going to be equal to mgh, right? So potential energy is mass times gravity times height. I'll just write that. So this is going to be 1 kg times 9.8 times a height of 3/4. And that's going to be positive because it's above the ground. So our reference level is going to be the Earth. And we're going to calculate the energy for this mass because it's going to change its position. So let's just do all the math on this, okay? So these are zeros over here, so that just goes away. Then we got a constant, right? Plus, what is that? 9.8 times 3/4. And that gives me, on my calculator, 7.35 joules. Okay. All right, so now that's great. So we know that the system has a total energy of a constant plus 7.35 joules. So now what we do is we have to go and find out, let's look at the other side of this equation afterwards. All right, so afterwards, there will be kinetic energy. And both the objects are linked together and they travel at the same speed. So I'm going to take a shortcut here and I'm going to say that the total kinetic energy is going to be 1/2 times the total mass of the system, which is 3 kgs, times the final velocity squared. And I know that final velocity is actually going to be the same velocity for both of the masses because they're connected by a string, right? And the string doesn't stretch or anything like that. So we can do that. We can combine the masses and assume they have the same final velocity. For the final potential energy, I'm running out of space here, but we'll say plus, and then I'm going to write underneath here, I'm going to say, well, the 2 kg cart is still going to be up on the tabletop. So basically, maybe I should sketch this. So the 2 kg cart is here, right? The 1 kg object is just about to hit the floor, like that. And so that top one, that 2 kg cart, has still the same potential energy of C, but the bottom mass has fallen and it's on the ground, so now its potential is 0. So that's going to be my final potential energy there. And that's great. So I'm going to write that down here. So this is going to be equal to C plus 1/2 times 3 is 3/2 V final squared. Okay. And then you can see right away that C cancels out, right? We probably didn't even need to write it because the top cart never really changes its height. And to solve for final velocity, you just have to solve this equation. 7.35 is equal to 3/2 V final squared. Okay, so we do 2/3 times 7.35. I get 4.9 is equal to V final squared. And of course, the last step is to take the square root of that. And I get 2.2 meters per second. Okay. And so that would be the final velocity of the system. So both objects end up moving with that speed. So just to kind of summarize what we did is we have a problem here. It's isolated, right? Because there's no friction. So none of the energy can leave the system. And all of the joules of mechanical energy you start with have to go into all of the joules that you end with. And that puts a limit, a mathematical limit on, what can happen on each side of the equation because the two sides have to be equal. And you can use that to find this final velocity. All right, so I hope that helps. And in the next video, I'll show what happens if you add friction.